So, next we will consider an example for this NFA to DFA conversion. Suppose we take the NFA that we have just constructed before. So, this is the NFA. Okay. So, now it is this NFA, if we are trying to run a DFA construction algorithm, then I said that first you take from the start state using epsilon wherever you can go. Like from this start state using epsilon you can come to the start state itself A, then B, C, D, then this H and I. So, this A, B, C, D, H, I. So, so that is the, if I say that is the set. So, this is the set that can be reached A, B, C, D, H, I. So, this set constitutes the start state of the DFA. So, for the sake of our understanding, we just give the name of the state as A, B, C, D, H, I. So, you can give any other name 1, 2, 3, 4 like that, but for our understanding we write it as A, B, C, D, H, I. Now, I have to see that on inputs where they can go from the states A, B, C, D, H, I, say from state A on 0 it is not defined, only from state D on 0 you can come to F, and if you come to F, from F on epsilon you can go to G, and using epsilon you can come back to A, and from A on epsilon now you can go to all the states A, B, C, D, H, I as we have constructed. So, I can say that from this state on by 0 you can come to the state F, and from F on epsilon transitions you can go to all the remaining states. So, this new set F, G, A, B, C, D, H, I, it constitutes the next DFA state. Similarly, on from this state A, B, C, D, H, I, if you see the transitions on 1, so you can see that from state C on getting 1 it can come to state E, and from there are no other transition. Of course, there is another transition from I you can make a transition on 1 to J. So, these are the two cases. In one case you have this, your C can take you to E and I can take you to J. So, naturally so this E and J, so they are the new states that have been identified. Now, from E and J on epsilon where can you go? From E on epsilon you can come to J, from G, and from G on epsilon you can come to A, and from A you can reach all these states. Similarly, from J there is no epsilon transition defined. So, from J you cannot go anywhere. So, you see that this is the new state that I can reach from this previous state on getting a 1. So, this since this state is not yet identified, so we just make it we make it a new DFA state, and you see that since this state J is included here, where J is a final state of the NFA, J is included here. So, J becomes the so this becomes one of the final states for the DFA. Now, now from this state, or from, let us come back to this FG, ABCD, HI. Now, what happens on a 0? So, since 0 transition is defined only from D to F, so from D it can go to F, and once you are in F, from epsilon transition, so you can come to G, from G you can come to A. So, essentially it gives rise to the same subset of states. So, so that way from 0, for 0 the DFA remains in the same state. From this state E, J, G, A, B, C, D, H, I. So, if you get a 0, then from this state D on 0 it will go to this state F, and from the F on epsilon transition. So, you can go to all the remaining states G, A, B, C, D, H, I. So, that way I get the same state for on 0. So, from this state if you get a 0 you come to this state, and from this this state E, J, G, A, B, C, D, H, I. So, if you get a 1 then it remains in this state. So, because on 1 from state C it will come to E, and from state E and from state I it will come to state J, and then on epsilon transitions. So, it will give rise to the same subset of states. So, this is the same state that is created for the DFA. So, this way we can convert one NFA into DFA using some algorithm, and you see that whether this DFA is more complex or not than the NFA. So, that depends on the type of regular expression that we are considering. In this case it is not complex, because now I have got only 3 states in the DFA compared to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 states in the NFA, and number of transitions are also less. However, as we have seen previously that this may not always be the case. In many cases, many situations, so it can give rise to the exponential number of states, the DFA. But for algorithms to the detection algorithms to run, so it is better if we have the DFA implementation. So, this way we will be converting the regular expression to NFA, and from the NFA we will be converting it into DFA. Some remarks on this NFA to DFA conversion. And NFA may be in many states at any time. So, what I mean is that suppose I have got a transition in the NFA from one state A, there is a transition on input symbol A to state B, and another transition on input symbol A to state C. So, if you are simulating this NFA and you are currently at state A, if your current state is A and the next input symbol is small a, then the next current state becomes the set BC. So, this is the meaning that you have, if you try to simulate the NFA, then you have to consider in terms of current set of states in which the system may be there, the NFA, the automata may be there. So, the NFA may be in many states at any time, but how many different states? If there are n states, the NFA must be in some subset of those n states, and how many subsets can be there? So, there can be 2 to the power n minus 1 finitely many, but exponentially many subsets, because it can do any of those subsets, like, so any of these if I have got, say, what I want to mean is, suppose my NFA has got a set of states S1, S2 up to Sn. Now, while you are doing the transitions, so it can be in any of the subsets, because from S1 it may be from S1 it may go to it may be going to S2 on A, and it may be going to another state S3 on A, or it may be that on S1 it goes to S2, S3 and S4 on A. So, this way, so these are the different subsets. So, S2, S3 becomes a subset, then S2, S3, S4 becomes a subset. So, these are the possibilities. So, in the worst case, so you can have 2 power n minus 1 different subsets that are possible, and it can go to any of those states, any of those set of subsets of states on a particular input symbol. So, and in fact, when you are doing this conversion from NFA to DFA, so what we are essentially doing is that we are constructing the equivalent set of equivalent subsets of the NFA, and then for each of these set of substates, so each of these subset of states, so we are calling it to be a state in the DFA. So, DFA, that is why DFA number of state can become exponential. So, in this case, so this can happen. So, you can it can give rise to exponentially many number of subsets. So, that makes it difficult for simulating the NFA, whereas for DFA we do not have this problem. A DFA, if you are trying to implement it, it can be realized by a 2-dimensional table T. One dimension is the states and the other dimension is the input symbol. So, what I say is that you maintain a table for a DFA, that this is the current state or present state, this is the present state, and you have got the input symbols, say this say A, B, so these are say C, D. Suppose I have got 4 input symbols, so these are the different states S1, S2, S3, etc. So, you just note down on say from Si to Sk, say from S1 to S2, there is a transition on input symbol A. So, I write here the next state is S2. So, accordingly we define that in this table I k I a equal to k, that is from state I on getting input A it will go to state k. So, I can maintain a 2-dimensional table where this T I a equal to k, or this S table corresponding to the state S1 and input A is S2. So, this is how I can represent the DFA, and for the DFA execution, for simulating the DFA, if we are in state Si with and input is A, we read T I a equal to A and skip to the state Sk. So, so this is how the simulation will be done. So, we have got an input stream. So, this is the input stream that we have, and at present the input pointer is somewhere here. So, if this is this symbol is A and the present state is Si, and we will consult this table and find out what is the entry for T I a in the table. So, and if the entry is say k, then we will update the current state to state k, and we will advance the input pointer to the next position. So, that way we can have a very efficient algorithm for simulating the DFA, whereas for simulating NFA you need to remember the current set of states. So, there can be a number of present states at which the system may be there. So, it makes it difficult. So, for example, this is the DFA that we have constructed, and if we name the states as S, T and U, S, T and U. So, I can have a table like this. So, there are only in my alphabet there are only two symbols 0 and 1. So, from state S on input 0 it goes to state T, on say input 1 it goes to state U. Similarly, from the state T on input 0 it remains in state T, on input 1 it comes to state U, from state U on input 0 it remains in state it comes to state T, and on 1 it remains in state U. So, this way I can have a very simple table that can represent the DFA, and then this DFA can be simulated as we have discussed previously. So, NFA to DFA conversion is the heart of tools such as Lex, Flex or JFlex. So, this Lex, Flex and JFlex, so they are some automated tools that have been developed by compiler designers. So, given they come as some utility in many of the operating systems. They were originally proposed to come with the Unix operating system, and later on many other operating systems, so they have integrated them as some tools for system development. So, if you are trying to develop a compiler for a language, so the lexicon analyzer part can be designed using these tools, and these tools, so they have the capability to convert NFA to DFA. So, they first take the regular expressions for the language for which you are going to get the lexicon analyzer, and then convert those regular expressions to their corresponding NFA and convert those NFAs to DFA. However, the DFAs can be large, can be huge, because normally it is produced as a text file, as a C program or C++ program or Java program, and the program size becomes very large, and it is very difficult to understand like what is there in the code. But we most of the time we take it blindly that okay, this is the code produced is correct, and since the tools are running for quite some time over the years, so they are time tested. So, there is very I should say the very little chance that there are some bugs in those tools. So, we can use those tools with a lot of faith on them, and most of the time what happens is if there is some problem, the problem is due to the regular expressions that we have written. So, there is some problem in the regular expressions themselves. So, this Lex like tools, so they trade off speed for space in the choice of NFA and DFA representation. So, we have there is a trade off between space and speed of operation. So, they do this trade off to see like what can be a reasonably good speed and reasonably good representation, the NFA or DFA. So, next we will look into one particular tool, lexicon analyzer generator called Lex. So, this is the original tool, as I said that this was proposed in the Unix operating system, this came with the Unix operating system. So, this is a lexical analyzer generator, that is it can generate you a lexicon analyzer given the source specification file. So, for the source specification file, so you should have this extension .l, that is a Lex source program. So, that is given to a lexical compiler. The tool is so we have got the tool Lex, and there are some more tools like some improved version Flex and JFlex like that. So, there are some improved versions, but what they essentially do is that they generate a C program lex.yy.c. This Lex and Flex, they generate the C program. So, that lex.yy.c, and this lex.yy.c being a C program, you can pass it through a compiler, C compiler, to generate the executable version a.out, and this a.out is a lexical analyzer for the source Lex specification file. So, if you now give some input to this program which follows the specification that we have in this lex.l, then it can accept it can detect the tokens that are appearing in the input stream and return those tokens, and like many other jobs can be done, some format manipulation and all, so everything can be done. So, this is basically a lexical analysis tool. So, this input stream will be coming, they will be given this a.out will analyze this input stream and it will give you the sequence of tokens. So, it will act as the lexical analyzer. So, we will see some sample form, sample structure of this Lex program. So, there is we do not have scope for going to a detailed discussion on this Lex tool, but what we will do is that we will see some overview that how this Lex tool operates or the specification file. So, this is the Lex specification file. So, this is the Lex specification file. So, we have got it has got three parts, the declaration part, the translation rules part and the auxiliary functions part. So, this declarations part, so these three parts they are separated by this double percentage marks. Okay. So, this is the format. So, all the regular definitions and declarations, so they should be put in the declaration part. Then what are the translation rules, like what do you do when you see a particular token, particular lexi matching with a rule, then what do you particular definition. For example, here I have put a regular expression say R1. So, here I have to tell for R1 what are we going to do. So, this rules part will be telling what to do with the when we perceive this particular thing. For example, if you find say some variable declaration, and then maybe the action for that is to install the corresponding variable into the symbol table. So, that way we can do it. So, and there are some auxiliary functions, so which may be used by these transition rules that we are writing here. So, these actions are written in a C code, and those C codes get integrated into the lexical analyzer tool, and as an output, so it produces the patterns and the corresponding actions. So, this ultimately generates a switch case type of statement, a big switch case statement, where for each of these translation rules, so it will have the corresponding actions which are given here. So, this way this Lex programs will be structured. So, this is a typical example. So, the first part, the definition part is up to the first up to this much is the definition part. Okay. So, here you can say you can definitions of manifest constant like LT, LE, EQ. So, this way you can define all the tokens basically. So, these definitions they can be useful for this parser. For the time being they do not have any meaning. So, this then comes this this regular definitions. So, this one is so we are defining a regular definition delimiter, which is blank, tab and new line character, and they are put within this square bracket, means it is the alternative. So, we the blank character, the tab character and the new line character. So, they will constitute the set of delimiters. Then the white space is a regular definition whose actual definition is like this delim plus. So, that is one or more occurrence of this delimiter characters. So, that is the white space. Then we are defining letter. So, letter is the definition, and the corresponding stream sequence can be this A to Z, and then and then small a to small g. So, that way we can have this sequence of characters giving this regular definition. Then digit is 0 to 9. Now, an ID can be letter followed by letter or digit whole star. So, I do not have any other symbol. So, it says that the identifier it starts with a letter and the remaining characters have to be letter or digit, and that is star. We can define the number. So, number is defined like this, that I should have at least one digit followed by a dot, okay, then then digit plus. So, if you have a dot, then you have got a digit, one or more digits, then there is a question mark. So, question mark means this entire thing. So, this part there may be 0 or 1 occurrence. So, that will take care of the situation, that is at sometimes we do not have the fractional part after decimal point. So, it will be taking care of that, and if you are having fractional part, then there has to be one digit before that. So, you cannot write like 0.25 like that. So, you have to write like 0.25, because this 0 in that case will match with this digit plus part, and then this point will be there, and this digit plus will match with this 25. Okay. But if you write like 0.25, then this first digit is not there. So, it will not be matching. So, this type of minute details may be there. So, that you have to see, and this whenever we are writing the specification, the Lex specification, we have to be careful at those points. Then comes the exponentiation part, that is 10 to the power part. So, this symbol E must be there, then we can have plus minus, and there is the question mark means it is 0 or 1 occurrence. So, we can have a sign or we may not have a sign. So, if we have a sign, that can be plus or minus, or if there is no sign, then that is also fine. In that case, it is taken as plus, then followed by digit plus. So, you should have at least one digit available. So, whenever you are writing say 0.25 into 10 to the power 5. So, you have to write like 0.25, then E5. So, you have to do it like this. So, now we have to come to the action part. So, for white space we do not have any action. So, no action and no return. So, it is simply written as no action. Then if we have the token I, if we have the symbol like regular definition if. So, if it matches with if the input is like if state if word, then it will return the token if. Okay. So, it is there. So, if it gets if it gets the sequence THEN, then this particular regular expression will match, and in that case the action part is to return the token then. So, in this way whatever regular definitions we have, so you can put it here, the corresponding regular expressions, and in the action part we have to give the corresponding C code. So, here it is returning else, as we know that the parser will call the lexical analysis tool for the next token, and this is how the tokens will be returned. So, this then else etc. So, they are all defined as tokens in the language, and so it will be it is the parser will know these tokens and the lexical analyzer will also know the tokens. So, it will be returning those tokens to the parser. Now, this ID. So, this ID whenever we are putting within this brace, so it means that this will be this definition will be replaced. So, it will be taking this definition and it will be replaced here. So, now it is doing it like this, that YYLVAL. So, this is a special variable that this lexical analyzer tool and parsing tool they will understand. So, it is some value of, it is the value of the token that is returned. So, I said that every token has got some attributes. So, this value is one of the attribute for the token, and the value is returned by the variable YYLVAL. So, we are setting the YYLVAL to be the install ID function will be called. So, that will be installing the corresponding identifier into the symbol table, and it will return the corresponding index of the table, and it will return the identifier. And in case of number, so it will be converting, it will install the number into the number table, and it will return the token number.